what the hell? This is bizarre that this pattern exists. It went from 0 to almost 100% immediately. I was amazed.
I'm extremely excited. Today we're going to be talking about a new paradigm of science, AI research in particular for math and physics, as well as do a deep dive into Professor Yang-Hui He's Murmuration Conjecture. Professor, what am I leaving out?
I think, well, thank you very much for having me again. I had so much fun talking to you last time, and it's great fun. So I got so excited about this new field of AI-assisted theoretical discovery, in pure mathematics and theoretical physics, that we're really entering a new era of discovery. And it's amazing. It's happening every week. There's something new that could potentially be transformative in the way we do science.
Yes, you said it shocked the math world, maybe even the physics world and the science world in general.
Yeah, absolutely. So, and I'm going to talk about a little bit more details about this, but just private companies like DeepMind, the fact that they're getting Nobel prizes, and and all these various AI companies, OpenAI, EpochAI, they're actually doing fundamental research with their models that are beginning to solve problems in real research and at the real research level. So this is quite exciting times.
Why don't you talk about how the landscape of research has changed with the advent of these new AI models? Now, there's a large class, like there's LLMs, but then there's also new machine learning techniques in general that you have uncovered and other people have uncovered. So why don't you just talk about that?
Yeah, absolutely. So, even when as I said, I think I mentioned in our first long conversation, I think I got into this thing as a complete novice. My background was in the interface between algebraic geometry and string theory, and in 2017, I was just beginning to learn from Coursera, just the very basics of machine learning, and so since then, I personally have evolved, and I have seen the field evolve. Of how far we can go, because 2017 was pre-ChatGPT, so this was just really machine learning of data from pure mathematics. But now we're much more advanced than this. We're beginning to benchmark. DeepMind's AlphaGeo 2, DeepMind's AlphaProof. They're beginning to show the science of reasoning. Whether they are reasoning, it's a purely philosophical question, which I have no right to answer. But what I'm seeing is that they're certainly beginning to outperform your typical undergraduate.
Mm-hmm.
And now EpochAI, which is another company, has launched this tier 1, 2, 3 problems, which are research level mathematics, the kind of problems you would give to a graduate student to give a collaborator or colleague. And I can show you some of that later, some of the stuff.
Yeah, I'd love that.
And they're entering their tier 4 phase. And in fact, I'm flying to Berkeley on Thursday to have a meeting with a bunch of other mathematicians to benchmark how far that their tier 4 reasoning machine can go. So this is really rather, it's happening. It's happening as we speak, how the landscape of research can be changed. Yeah, sorry, yeah.
Yeah, I think that's in part why, firstly, it's an honor to speak with you again. Our last conversation went viral. I think that's this whole AI-assisted research in math and physics is part of the reason, because our last conversation was quite specialized in nature. It just means the audience loves you, loves hearing from you. I also love speaking with you. You also have some books. In 2018, you had a book published called Topology and Physics, and I believe that's followed by your textbook in 2020 on machine learning and pure math.
Right. Yeah, so the 2018 one was when I finished and posted on Archive, which is a very kind thing that Springer lets me do. But then the final book was the first textbook on... I wrote that book primarily to teach myself machine learning and AI, because I was a complete novice in this, and it was just I wanted to share this experience as a theoretician, as a mathematical physicist, how to share with this community, how to even begin with learning about machine learning and AI and this advanced data techniques. But now I think the field has progressed way beyond that in the last 8 years, and we're all very, very impressed with how we as a community, we're all very impressed with how fast this thing is going. And so it's a great pleasure talking to you. As I said, I'm a big fan. The kind of depth that you go into is quite different from the normal science communication, because you really, I like the fact that you like to dig deep in your topics. I mean, I guess even more advanced than quanta, which is really good. There's not that much out there that does this. That's why I appreciate what you're doing so much.
Okay, well, let's dig deep. What are some different ways that people use machine learning? So, for instance, Terry Tao uses it as an assistant to proofs, but also to generate conjectures and perhaps to even point to existing tools that he may not have heard of. And those are more of the LLM sort. Then there's another sort of just finding patterns in large data sets, and that connects to your murmuration conjecture. Is there a third category?
Yeah, that's right. So I was just trying to, I think I outlined this briefly last time. I'm just trying to, because this is exactly the kind of thought process that's going on, how to categorize the different approaches. And of course, they're all interrelated, and it's hard to delineate them. But so this is my top-down mathematics is this intuition-guided basis of mathematical research. And this LLM approach is what I call meta mathematics, and this is kind of LLM assisted co-pilots that Terry Tao is talking about. And then this third category of bottom up, where not necessarily any AI is involved. I'm thinking about things like lean provers and proof as co-pilots, where you just have millions of lines of code, and sooner or later somebody's going to process that by AI. The interplay between these three directions, and between that and the human, is clearly beginning to change the landscape of mathematical research.
Now, before we get into your presentation here, you mentioned on another talk, on another, either an article or a podcast, I don't recall from my research, that there are two types of researchers. One is a bird and another is a hedgehog. And you're more of the type that likes to fly and connect. I'm also similar. So I think that's one of the reasons we get along so well and that the audience loves you. But tell us more about this.
Yeah, I think there are various tributes to this quote. I think it originated from a Greek fable where the fox and the hedgehog are compared, where the fox knows a lot of things and the hedgehog likes to dig in. And I think the great mathematician Arnold made a reference to this in Classifying Mathematicians, where he calls things like, one is an eagle that flies and tries to see the landscape, and then the hedgehog digs deep to one particular problem, solves it. I mean, there's no particular, neither is superior to the other. It says we definitely need both, and each mathematician can function as both. But certainly, AI is helping us in both personalities, simply because there's so much literature out there. The AI can have an overview of what everything is in terms of the literature, and there's so much technical detail. There's some very boring parts of the proof that you just simply don't have time to iron out, and that can certainly be helped by LLM models. And it is beginning to do that. I was actually just at a conference last week in Exeter. There was a conference called the Impact of AI for Mathematics, where the organizer Madhu Das, and she was saying that she's a number theorist, and she said she's just recently completed this very complicated paper where she had to prove a lemma. And then what she did was she knew there's another lemma which has got to be true.
Okay.
And so what she did was she copy and pasted the entire proof of her lemma. It's a bit technical stuff into ChatGPT 01. And then said, now then copy the lemma and said, can you supply the basic proof strategy of this lemma, which I know to be true? Now, to be fair, this is very far from automated reasoning. This is just language model. And then importantly, what she did was, and then she went line by line, symbol by symbol, the proof that ChatGPT gave her for the big long lemma. And it was largely correct. And with a bit of prompting, she was actually able to nudge out a complete version of that proof. And then that was done. I mean, so it would have taken her much longer to have ironed out all the details herself. So
Wow.
this is really rather impressive. And this is only because of O1. And O1 came out, I think, this year or end of last year. So it's really transforming the kind of stuff. The boring stuff you can delegate, and also the pattern recognition part you can also delegate. So we become like superhuman all of a sudden, and can interact with these agents who can help us actually do research and not just do very elementary problems now, but serious research level mathematics.
Why don't you talk about some of your personal use cases? So do you use ChatGPT more than Claude, or do you use Gemini more than the others? Like, what is your mixture?
I actually, in terms of research, to be honest, prior talking to her, I never even really played around with this kind of LLMs to help with my research. I didn't know that was possible. I know, it's kind of thing you can, if you want to know very quickly a topic, you can go to Wiki, you can Google, but indeed, ChatGPT or DeepSeek will probably answer your question very quickly. If there's some theorem that you just forgot, or there's a field that you really don't want to know about it, DeepSeek will summarize it much better much more efficiently than if I went to some expert and wasted his or her time and just have that. The process is much more efficient if I just wanted a very quick overview of some even a specialized topic. So that's been very, very helpful to me.
So it's only been 3 years since ChatGPT came out, and already we're seeing this massive change in the landscape.
Yeah.
Do you imagine that 3 years from now, or let's say 10 years from now, that the role of the future academic or intellectuals or mathematicians, if you want to specialize, will be that of a decider or director, like a curator, rather than a doer? So the doer is the one that right now we use computation, we use syntax, we come up with some proof, but the decider would be one that just, okay, it governs. It says, this is what you should do.
Compute already helped us a lot by the end of the 20th century. So no professional mathematician really goes by the 90s and early 2000s. No professional mathematician, for example, does boring integrals anymore during research, because that's completely outsourced to, say, something like Wolfram Mathematica and then later Sage Math, because this is just boring and we know how to do it. It will take us many hours if we really want to grind out some technical integral. Of course, I'm not saying that you shouldn't teach undergraduates integrals anymore, because that's part of the learning process, and it's still important to teach undergraduates this kind of thing. But no professional mathematician will start. They're really boring and horrible things, like even the simplest thing, sine 17 X. Nobody really wants to go on it.
Oh, geez.
It just type into Mathematica, because if I just need that result very quickly so I can supplant to my next step of what I envision in my paper, I'm not going to waste a couple of hours trying to integrate something very elementary. And I'll probably even get it wrong. There'll be factors wrong. So that already transformed it. So I can see 10 years from now, simple, basic, maybe I'm being conservative here, but simple bits of a proof or simple bits of a derivation can just be outsourced to the likes of ChatGPT or DeepSeek or something even more specialized. We don't currently have an LLM just for mathematics. That's surely going to come very soon. I'm sure the Frontier Math project by EpochAI will start providing this kind of services.
Okay, well, let's get into your presentation on the AI Mathematician.
Yeah, sure. Well, thank you. So I guess, last time we talked about various things, and I just want to share more in this chat some of the capabilities, both in the terms of top down and bottom up of what we're looking at. And to be honest, even since our conversation, which was 5 months ago, the field has advanced significantly, which is very, very impressive. So just briefly, as I was saying last time, and I just as I also just mentioned, I try to classify this in this review article. these three directions of mathematics. Of course, they are intertwined, and the memoration conjectures that I did with my collaborators Lee, Oliver, and Postnikov is really a very good example of this top-down, and I'll explain why. This top-down mathematics is one that I want to emphasize here, and then I will go back to just refresh people's mind a little bit about how people like Terence Tao and all these great and top minds are doing a proof assistance in terms of what I would call bottom-up and mathematics. This is a very, very interesting point where I want to emphasize, the typical mathematician, and that includes theoretical physicists. Historically, we do things top down by just looking at patterns and spotting patterns, and we do many things in terms of practice before foundation, and this is very important. This is something that can't really be formalized, because linguistically trying to formalize mathematics, and which is an extremely important program, right? And all of these benchmarkings of problem solving using large language models, this is when you have a precise, well-defined problems and trying to find a solution.
Yes.
But the history of scientific discovery is certainly not that. I would say probably more than 50% is actually finding the problem, or have a vague notion of something before you can formalize it.
Can you give an example?
So, for example, so here, giving an example. So, for example, Newton invented calculus without any notion of what even convergence means. He just had this intuitive idea of motion. And then because it was Newton, he intuited there's this thing called derivative. This is way before we could even have epsilon delta limits, which came in the 19th century, almost 300 years later. And algebraic geometry is something closer to my heart. Algebraic geometry was just started with the Apollonius and Euclid, with just shapes and stuff, and we can intuitive the kind of theorems we want to prove. Before this Bourbaki school in the 1950s and 1960s, the height of the Bourbaki school tried to formalize that in terms of definitions of fields and rings and polynomial rings and ideals. And this is how theoretical discovery has always happened. In some sense, this is the reason I want to emphasize this bit is not only just because this is one I'm most familiar with and the one that I suppose I've been mostly involved with. Another reason I want to emphasize is that it's hard to imagine how AI can help us with this, because it's so vague and it's so human. And there's a lot of mistakes. And if you train some language model, there's not even any data to train on, because these are not formal proofs. These are just grasps of ideas of intuition. And the point I want to make that is that even in this direction, AI is beginning to help us.
Okay, so let's imagine we're back in the 17th century with Newton.
Yeah.
And Newton was saying, okay, I want to come up with something like calculus. He didn't even have that term. He just had this notion of motion, like you said. What would Newton do with an LLM? Like, what is your vision? So, I don't usually stop mid-conversation about mathematics to talk about metabolism, but I've been using something that's made an appreciable difference. It's called Cell Being by Verso. Summer's coming up, and if you're like me, getting lean while juggling work, stress, and everything else isn't exactly straightforward. I train, I eat well, but as I age, as we all age, fat loss gets harder. Cell Being uses research-backed ingredients that help your body boost NAD levels. NAD, by the way, is crucial for metabolism, energy, and even DNA repair. However, there's a large added benefit here to Cell Being. This formula also helps regulate hunger hormones and supports fat breakdown. Basically, it tells your body to burn more and crave less. Since taking it, I've noticed I'm not as peckish, I feel more clear-headed, my energy is distinctly more stable throughout the day, and I'm discernibly quicker mentally. I haven't changed anything else about my supplement regimen, I've just added this, and it's helped me stay consistent without forcing it. Also, Verso third-party tests every batch and publishes the results, which matters to me personally because this way I know exactly what I'm getting. So, if you're looking to dial in your energy, metabolism, and shed a bit of that stubborn fat before summer, Then check it out. Head to cell.ver.so/TOE and use the code TOE, so TOE, to get 15% off your first order. That's cell.ver.so/TOE, cell.ver.so/TOE. The code is TOE. Thanks to Verso for sponsoring this episode. What would Newton do with an LLM? Like, what is your vision?
That's an interesting point. So what Newton would do with an LLM, if he had an LLM, which was certainly to process all previous literature. Now, to be fair, at Newton's time, somebody like Newton could read almost the entirety of any relevant literature up to his point.
Mm-hmm.
And I'm thinking about everything from Euclid's Elements, Galileo, bits of Kepler, and he certainly wouldn't have that. Then you just go and you just go and read it, and that's fine. But now literature has grown so exponentially, there are no more human Newtons, that could possibly read the entire literature of a field, and that's where LLMs could come in to help. So this is in the LLM space of discovery. You can summarize literature, and you can try to create new possible links between literature, and this is happening now. I think Llama, Llama, which is LLM for math, like Llama, double L. Llama is something. It's an AI tool that's beginning to digest the archive, for example. And on the other hand, that's the LLM side of the story. And now, what about the other half? Is how could Newton, based on mathematical patterns, and he did have a lot of patterns. It would be things like this would be mathematical data. So certainly that he had data in terms of theoretical and experimental physics, where you could measure falling, the rolling of the kind of stuff that Galileo did, the rolling of balls along inclined planes, that kind of data. Or he had the astronomical data of Kepler, but he also would have had mathematical data or Platonic data. I like this word Platonic data because it's pure. The kind of data that would be like sets of polynomial equations in two variables, which he actually tried to classify himself. How many cubics? Because he knew about the conic classification problem. And he would look at these things, and then he would spot patterns. And this kind of stuff also gave rise, I would imagine, I can't imagine, the mind of Newton, but I would imagine he would look at vast amounts of such data and then try to formulate a theory out of it.
Okay.
And that's kind of really nice. So that's an LLM independent thing. This is just pattern spotting. So like Newton, there are these things called Newton polynomials, which expresses, it's a technical thing, which would be Newton, certain symmetric polynomials in multivariables being expressible in some basis. I would imagine Newton would have written pages and pages of this stuff and spotted a pattern and then tried to prove a general theorem, which is now the theory of Newton polynomials.
I thought where you were going was this amorphous ideation with an LLM. So, for instance, Newton would say, okay, I have balls coming down an incline. I don't have a precise formula for velocity. I don't even know if velocity is a great concept, but I noticed that it moves faster, but it can also, so that may be associated with something I would call acceleration. But then there's something else like an impact, which I may call force. Can you help me with this? Is there a way to make this concrete? Like to take something that's ill-defined and make it well-defined? I thought that's where you're going. Do you think LLMs help with that, or is that not what you were thinking about?
No, I think that definitely helps a bit. We're not quite there yet, I think, where we could just start asking LLMs and say, here's the literature, digest it all, and give me new possible links. But we are actually not insanely far away from that goal now, because the LLMs are getting so good at doing this sort of thing. So it's actually not impossible. In some sense, Newton would, the mind of Newton is something like that. I guess, let me see my next slide. I think I do mention, I do mention that the another mind as great as Newton and Gauss, and I will give that example in a minute as well.
All right, let's get back to the presentation.
Oh, so I think I can't remember whether. Speaking of Newton, I can't remember whether I talked about this last time. If not, this is a joke worth repeating again, which is what is the best neural network of the 18th century? You could argue the 17th century was Newton, and the best neural network of the 18th to 19th century is clearly the brain of Gauss, right? And that's another. Here's a very very good example as well of just top-down, intuition-guided mathematics. And I might have mentioned this last time, but it's worth repeating. So what is the thought process of this great discovery here? So everybody knew about the primes. Euclid already proved that there's an infinite number of primes, and the proof is very very beautiful and it's kind of intricate. It's the first thing you would teach in a number theory course. It's not obvious at all there's an infinite number of number of primes, but Euclid had this proof by contradiction argument why there should be an infinite number of them. So Gauss certainly would have known that proof. But Gauss wanted to know more, and it's been 2,000 years since Euclid. Gauss wanted to know about more details about the distribution of primes. We know the primes get rarer and rarer, even though there's an infinite number of them. They do get rarer and rarer. How rarer do they get? And he just devised this function, which we now call the prime counting function, P of x. It's a terrible name because P is pi, but it got stuck in the literature. And P of x is just simply the number of prime numbers less than a given positive real number x. So that was one of his insights was to devise this function which is now continuous because primes are inherently discrete. And this is very interesting. He plotted this and he looked at this curve. He invented regression, apparently, in order to do a curve fitting because he needed. This is all done at the age of 16. He invented regression to see, well, what is the best shape that fits this? And all of this done by hand. And he even had to compute the primes into the hundreds of thousands because the tables stopped there. And he even got some of them wrong because it's a very boring and tedious computation. Imagine what Gauss could have done. One, if he had Math Sage or Mathematica, he could have. How much more conjectures would have raised, right?
Well, the problem with that is that if he has access to the modern tools, he also has access to TikTok, and it's not clear if Gauss would be bored.
Yeah. Well, let's hope that because Gauss is Gauss, he wouldn't waste his time doing becoming like I don't know, doing like watching YouTube videos, but and watch more meaning. Maybe he would. Maybe he'll watch meaningful YouTube videos, like other conversations, like the kind of conversation you put on Theories of Everything.
Okay, great.
But anyway, he would do this thing, and he looked at this P of x, and he says, it's clearly x over natural log of x. You won't be able to see this just by looking at it. So he really actually had to invent regression to do this. And so statistics was a side product of this problem. As far as I know, but this needs to be checked with the real historians of science. But at least that's the story here. And this is just crazy. Like, what do you even do? And the proof of this fact was given 50 years later by Adamard and de la Valle-Poussin because you had to wait for Cauchy and Riemann to invent complex analysis in order to give a tool to prove this fact. So how did Gauss know this? Based on just at the time would surely be called large data, right? He really went into the tens and 100,000 range in order to spot this kind of patterns. And it's just amazing. And I can plot this because if you just plot the first 100 or so, it looks kind of like a log or kind of like a line or something. But you really need to go into the thousands or tens of thousands range in order to do something like this. So amazing. That's exactly the kind of top-down guiding intuition. There was not even the foundation to prove something like this until years later. Riemann as well. I mean, a great example. Riemann hypothesis, which is arguably the most famous open problem in all of human intellect, and is certainly the one that we all bow down and worship. It's about so the Riemann hypothesis has so many implications in mathematics. It's one of the Millennium Prize problems, and the Riemann hypothesis it's so important precisely because there are now probably tens of thousands of mathematics papers whose first opening line is, let us assume that the Riemann hypothesis is correct, and the rest of the paper. So it has so many implications. So that's the kind of conjectures that are great, that it has implications to so many other possible results. The interesting about the Riemann hypothesis is that it appeared as a footnote in Riemann's paper. Riemann was just doing the Riemann zeta function precisely to address a similar problem to the precise distribution of primes, and he wrote in a footnote that I checked the first couple of zeros, and they all have real part a half. I believe that this is true, but I don't really need this result right now. You can see that amazing footnote. And then that we just said, I can't think about this right now, but I think this is kind of interesting. And then that was the birth of that. Now, how did Riemann intuit something like this?
Well, these number theorists and their margins.
Exactly. Number theorists love margins. Exactly. Now, yeah, I never thought of it. That's a good point. But that's an actually extremely good point you mentioned. They're written into margins because they haven't been formally proved. We put into form but if it's structured, it would be bottom-up mathematics and it would be in the main text. And often these marginalia are just afterthoughts or just sparks of genius of these people who would just relegate this thing to a side comment. And that kind of intuition leads to centuries of research. So that's a very good point you raise about how the difference between margins and formal text, because papers are written, whether it's pure mathematics or theoretical physics, papers are written in a very structured backwards kind of way, from quite different from the way they're reached in this intuitive kind of way. Yeah, so that's a good point. Yeah. And then this doesn't stop, and this is something that the Memoration stuff will get more into, which is this BSD conjecture, which is another Millennium Prize problem. This is another one that carries a $1 million tag. And how did this come about? And I will talk more about what the BSD conjecture is. This is Brian Birch, who is still alive. He's, I think, 90 something. Mathematicians are very long-lived because they're happy. And the Birches went and died in the 60s. They're in the basement in Cambridge, and they just plotted loads and loads of data for ranks of and conductors of elliptic curve. Now, lots by 1960 standards would be in the order of hundreds to thousands. The LMFDB, which I'm going to talk about in a minute, is a database of 3.6 million curves. So we've progressed quite a bit. 3.6 million is a kind of data scale where you could really train things on, and that's where I could really come in. And this just in the stop. They plotted this and they raised this conjecture. They noticed a certain pattern between R and ranks, so these technical terms which I'm going to define in a minute. And that was the birth of yet another great and foundational problem. And this is regarded as central piece of mathematics as well.
Okay.
And these are all intuited, if you wish. Right. So just one quick slide. I got into this because of algebraic geometry. And so I think I mentioned it in the last talk. Just trying to see how machine learning can help us spot patterns, if you wish. But I think since 2017, I grew a lot alongside with my son. We both grew. Mm-hmm. He's growing very fast, and I'm growing intellectually just to digest this field. And it's a humbling experience just to see this vast interaction of so many different people and experts. And so again, I like to thank all of my collaborators. Now I can't possibly read out all the names, but is where the QR code comes. Scan this QR code. There's a long will point you to a Google Doc where I will try as much as possible to keep up to date all of the names and affiliations and the papers with my co-authors, so you can thank them properly. At some point, now this is an interesting part. I wanted to ChatGPT to generate the list of these people and search the internet and find a picture of each of them and give them affiliation, so to save me the time of typing them out. So we're talking about almost 100 people.
Yeah, we can talk off air about that. I can code that up for you extremely easily.
Okay, but what is really interesting is that ChatGPT did a terrible job. It found random affiliations of people who didn't exist because they're doing LLMs, so it's matching them to it's confusing my collaborators. So I couldn't possibly credit ChatGPT for this. And so this is a very early thing. And also they just couldn't. ChatGPT could not produce the correct photos of any of these people. So we are limited. So as excited as I am, I must point out limitations to all of that. I
Yes.
tried DeepSeek, Claude, I tried them all. None of them could even answer this problem, which should be a simplish problem.
There are ways of using the agent or the LLM to interrogate itself so that it can double check. So we can talk about that off air.
Oh wow, that's that. If you can help me with that, it'll be great because this is something. This is obviously something AI can help us because this is boring and it just needs to be done as even part of scientific discovery. It took me an hour to find that LLMs were useless in this, but that hour I could have tried to do something more meaningful. But you would take hours if I would just do it properly and include copy and paste pictures. It would take many hours, and that's why we're so. This is just to tell you we're not quite there yet, even with a simple task like this. So surprisingly, it can help us with mathematical discovery. But all of this will change very quickly. Um, and that's the book I think you mentioned earlier, which is this. This is the book of my learning experience, trying to learn about machine learning. And this finally came out, I think, there's an archive version in 2018, and I think it appeared in 2020. This the landscape. This is from everything from machine learning, and then this editorial in 2020. So now let's get back to the real meat of the subject, which is I believe this this is still part of this review. I was trying to say I try to emphasize that bottom-up mathematics is a natural language processing because this is however you want to define it. Meta mathematics is LLM, and top-down mathematics, this intuition guided thing, at the end of the day, is image processing. I like this image processing idea, which is any mathematics, any mathematical data, platonic data, if you wish, at some level is an image. You can pixelate it. I like this image analogy because the great David Mumford, who is also a Fields medalist, even back in the 90s, after he got the Fields medal, he stopped everything. He got the Fields medal for doing topology in K-theory, if I remember, it's algebraic topology. And then he switched fields completely, dropped mathematics altogether, and started working on computer vision. And now that I've read more of his recollections, he blogs as well. He's a very excellent blogger like Terry Tao. So David Mumford, he said the reason he got into this computer vision thing was, I think he was really having early visions of how AI can help with research, because he was trying to imagine the human mind being an image processing machine. What does a mathematician actually see? The mathematician is beginning to have mental images of formulae. There is this transformation process from what you see as abstraction, as mathematics, into a mentally constructed image. That's why he was so interested in vision. And that image in the mind is somehow, well, now I guess in today's language, this will be the latent representation of your data.
You know Hadamard, how he had a book on how mathematicians think.
Oh, I heard of that. I have not read that. That's kind of interesting. Is that the same Hadamard as the Hadamard de la Valle Poussin Hadamard? Oh, interesting. Oh, cool guy.
Yeah, and I'm wondering if he did a historical analysis for Euler, because Euler was blind for half his life or something like that, some large portion of his life. So I'm wondering if Euler still used mental imagery to formulate or solve his problems, or if he had to then abstract to something else.
Absolutely. It's quite imagined how I had a student once in Oxford a few years ago now. She was quite remarkable because she's completely blind. I think she was blind from an early age. So she sat through my lessons without being able to see anything. She had to picture what I was saying and then digest it all in her head and do all of the mental calculations in her head.
Interesting.
So I was wondering, what was she actually doing? And she did fairly well in her final exams with being completely. She needed somebody obviously to translate whatever she's had to dictate to someone in yeah. So it was quite remarkable that that I got to know the student. But anyhow, that this is a but my image processing is this kind of thing is now that I read Mumford, I'm beginning to think why I was beginning to think that all of mathematics is there's all of top down, all pattern recognition is an image processing problem.
Uh-huh.
Yeah, this I guess there is this old debate, and this involved all the grades like Atiyah and Digraph and Hitchin and Witten, all these people. Is physics or is theoretical physics or is mathematics inherently is nature um, algebraic or is it geometric? So
Interesting.
this top-down mathematics, this is a debate. Newton was clearly geometrical. He had such a distaste and disdain for algebra because it's meaningless symbols to him. He made some comment about algebra is this. I can't remember the original quote, but he will say something. It's a very disgusting thing that you had to resort to this meaningless symbols. He was very very pictorial. His proof, what we now call the Gauss theorem, about integration over spheres. This was just some about a gravitational body exerting a force on an external object. Gauss would just surround this by and then uses Gauss's law. But Newton actually integrated piece by piece and used all these intricate pieces together in a diagram and got the same answer. It's the kind of horror show you would never do because Gauss's law, the Gauss's theorem is just one line. You just do this integral. But Newton actually had to piece together. So Newton was definitely visual. Roger Penrose is definitely visual. Penrose, my last conversation with him, he almost said, I think, I just in case I'm putting words in his mouth, but I believe he says something like, if it's not intuitive and if it's not geometrical, he doesn't even accept that as a proof.
Hmm.
And I think Conway was like that as well. This is one of the reasons why Conway never really accepted Richard Borcher's proof of the moonshine conjectures, because Borcher's used this very strange um, this vertex operator algebra. I think you had a conversation with Ed Frankel about this.
And Borchards, actually.
And Borcherds, yeah, exactly. But the Borcherds, he borrowed this piece of completely crazy stuff, vertex operator algebras, and had this beautiful structure. I mean, it's obviously awesome and brilliant. He got him the Fields Medal, and he was able to use that to prove the moonshine conjecture from Chi. And Conway, to my knowledge, who was it who told me this? It was gosh, the previous director of the IS, who was a good friend.
Robert Dijkgraaf?
The one before the
Oh.
gosh, Goddard, Peter Goddard. Peter Goddard knew Conway very well, and he was telling me that Conway never really deep down accepted this proof of Borcherds because it's not visual. Conway is this very playful guy, as you can imagine. He wanted everything to be pictorial. He wanted to see his lattices. So anyhow, in a way, this diagram puts geometry in this direction and puts algebra in this direction.
Well, how is Conway visualizing the monster group?
Maybe in terms of the Leech lattice, he had this picture of the Leech lattice. To him, the monster group is some extension of the automorphism of the Leech lattice, which I guess in a way that's how he and Gries and Reba originally came up with monster. It wasn't by very hardcore this whole funny business of classifying simple groups that it. He really intuited it in a way. He got this group out by doing norm 2 lattices, and he was able to see the symmetry, the group of symmetries of this lattice, and that's a remarkable thing. Yeah, it's just unfortunate that whole generation of people are that generation of this lattice, early computer algebra, finite group people are slowly dying out. Conway is dead, Norton is dead, and my own dear friend John Mackay, who started Moonshine, passed away. I wrote his obituary because I was his last close collaborator. He actually became a grandfather figure to me. He became, he saw my kids grow up.
Interesting.
And Mackay would tell me the stories about how he was interacting with Conway and how all of that people, how Birch and Mackay is also here's another crazy. That's another whole conversation about what is this bizarre intuition that Mackay had. If there's anybody in the later part of the 20th century who had a almost Ramanujan-like intuition, would be John Mackay. In a way, he's an unsung hero because he would just look at lists of numbers or look at pictures and graphs and see, but this field is related to this, and that is very much like this. He's AI before AI.
Even physicists?
I think that's a whole different conversation. We're gonna have to do part 3 and 4. This is okay. I get very emotional when I talk about John because he's like he's a very much like a father figure to me.
Well, the next time I'm in Oxford, we should have a part 3 and 4.
We have a part 3 conversation just talking about moonshine conjectures. From the perspective Mackay, I know you certainly. Oh yeah, and he pronounces his name Mackay, not Mackay, even though it's written down as Mackay. He insisted on being called John Mackay. I know you chatted with Franco and you chatted with Borchards on Moonshine and that stuff, but it's unfortunate that he passed away before you started all this thing. He passed in 2022. Because he had a very interesting knowledge of that world, of moonshine and stuff. But anyhow,
have you heard of stone duality?
Stone?
Yeah, stone duality or a stone type duality.
No, not at all. What is that?
So it's a duality between topology and then Boolean algebras, which some people see as an analogy or an equivalence between geometry and then syntax, or something more algebraic.
Oh, interesting. Oh, I'll have to look into that. Thanks for pointing out. I didn't know. Is this like the stone of the Stone-Weierstrass theorem stone?
I believe so. You got them all correct. Yeah.
I don't know. Okay, I just didn't know there was this stone. This is called the stone correspondence, or
yeah, stone duality. Yeah.
Duality. Oh, I would love to see it. Sorry, I just bumped in my. I'd love to see that. Oh, interesting. Very interesting. Anyhow, so back to our current story. So in 2022, ChatGPT actually, as you know, pertinent to this conversation, ChatGPT passed the Turing test, which I'm very surprised it was not on every single newspaper headline. I don't know why this wasn't emphasized either. We can't really. I mean, Turing test was a big thing. I think that the fact that ChatGPT passed the Turing test just simply showed that you don't need reasoning or understanding to have intelligent conversation.
Mm-hmm.
Maybe it says a lot about humans. It says more. ChatGPT passing the Turing test says more about humans than it says about AI. I think we give too much credit, to what meaningful conversations are. But this, sort of as a response to that, we organized a conference in Cambridge with loads of people, and you can probably recognize some of the names: Buzzard and Birch. We tried to formulate something that's more stringent than a Turing test for AI guided discovery. And so I reported this with my friend Birch as a Nature correspondence. And this is again, I can't remember whether I talked about this in our. Did I talk about the Birch test?
Yes, the Birch test plus or the Turing test plus was the Birch test.
Yeah, it's the Birch test. Yeah.
Last time. So we'll put a link on screen for the last conversation in case you're just tuning in and you're wondering. It was a wonderful conversation. And I believe we talked about, let's see, the Birch test, bottom up, top down, metamathematics, and even classifications of CY manifolds, and then this database construction.
Right. Okay, so I can pass with the B. So this is AI plus N for the Birch test. So let me just, I guess I'm very good at digressing. Sometimes I digress so much that I don't even remember what I'm digressing on anymore. But the point is, this is clear signs of ADHD, but I've never had it.
As you mentioned in speaking about these shower thoughts or the margins, the digressions are sometimes more meaty than the meat.
Often, yeah. But back to this AI guided system, was the discovery, which in terms of AI assisted top down intuition guided discovery in mathematics, there have been various candidates in the past 8 years or so. Some of the ones, of course, everybody talks about this beautiful paper in this DeepMind collaboration by Alex Davis. Alex comes here a lot because DeepMind is in St. Pancras, which is a 30-minute walk from this institute, which is kind of very nice. We have a nice hub in London for this sort of thing.
Google
And
DeepMind isn't in California?
there's a London office.
Oh, okay. So there's a branch at least.
I guess that yeah, there must be, yeah. So Alex is actually in London. So that the Davis et al. Paper, and DeepMind is
Cool.
so he comes very regularly. Of course, he can't, because he works for Google, for DeepMind. He can't tell us exactly what he's working on, nor can he tell us what the next project will be. But at least he can summarize what the state, what's going on in the tech world, which is kind of interesting. The fact that Nobel Prizes are being given to non-university organizations, which is
Right.
just very, very nice. Which is what this organization is. At some point, that's another whole conversation again. So I think I mentioned, yeah, Asterisk. I think I mentioned to you last time that these are the rooms where Faraday lived. Okay, so we're very lucky. The London Institute, we're at we're the second floor of the Royal Institution, where the likes of Humphrey Davy and Thomas Young and Michael Faraday lived. So I'm very fortunate to be in this space to work and try to get this in. But one of our themes, the reason I mentioned this, one of our 4 research themes is AI for theoretical discovery of this institute. And it's kind of, and we're independent of the universities so that we could devote our time fully to research. That's kind of thing.
So how does this lead to the Murmuration conjecture?
Yeah, I promised to tell you about Memoration. Yeah, so this Clavier manifolds, which we spent so much time talking about last time, this is because it was my bread and butter as I was growing up as a grad student. So that was clearly the first thing I'm going to apply machine learning to. The kind of experiments of using neural networks to predict topological invariance of these varieties in the image processing kind of way immediately fails the Birch test out straight because it's not interpretable. Sure, now it's been improved to 99.999% or whatever it is, but it's useless to a scientist. It just simply says that, oh yes, there is an underlying pattern, but how do you actually extract anything meaningful from that pattern? That's the main question. So the closest so far, and when I say so far, it really, this could change in a couple of months. Oh, you have no idea because the field is growing so fast. The closest so far in the last, oh my gosh, it's almost a decade. I guess my son is 8 now. In the last decade of all this AI discovery, there's been hundreds of papers now on various things, like on how do I use machine learning to do this in number theory, in theoretical physics, in quantum field theory. There are literally hundreds of papers. Now, the one that really made Buzzard and Birch happy is this Memoration conjecture, and the discovery process of this is something that I would like to see, or at least that this is sort of the state of the art of human machine interaction. That's why it's so close to my heart. And this is joint work with Qiuhuan Li, Thomas Oliver, and Alexei Potsnikov, and now with a paper to appear with Andrew Sutherland, who is the guy who set up this LMFDB. So I think I mentioned last bits of machine learning experiments in number theory. Providing can AI predict primes? No, we're certainly not at that stage. I'm not saying you can't. If an AI can detect a pattern in primes by itself, then we'll be at the next level in not only proving the Riemann hypothesis, we would also crack every single code in every single bank in the world, because that's all the cryptography is dependent on this.
So wait, what's the main impediment for AI to not predict primes? There's a large data set there.
Yeah. So actually, that's a good question. And the short answer is I don't know. I've certainly fed in millions of primes into whatever representation into a neural network of whatever architecture. I just simply asked it to predict the next one. It does terribly on this. I think somebody's even written a paper on this called "Why Prime Prediction is So Hard for Neural Networks." I can't remember the precise networks. I think at some level it has this again goes back to the Riemann hypothesis. That's why the Riemann exact patterns in the distribution of the zeros of the Riemann zeta function in the critical strip will give you precise patterns in the distributed primes, and people have proven statistical statements about the distribution of the zeros that they're truly stochastic up to some level. I'm not an analytic number theorist, but basically there is so much noise or truly stochastic randomness in the distribution of the zeros of the zeta function that it's very difficult if you try to train. In other words, training a neural network of the zeros of the zeta function is like training it with noise.
Interesting.
Something fundamental had it, but it could just be that this representation we're using for the zeta function is not very good. We should dig deeper. But you need almost another. Of course, if you find the right representation that would give a very good pattern spotter, that representation is the new mathematics we're looking for.
So, speaking of classifications, as we're both fans of classifications, is there a way to map this problem of doing an image processing for prediction of primes / the Riemann zeta function zeros? Is it mappable to P versus NP, or is it a new class like, okay, problems that can be solved with image recognition or image prediction versus problems that can't in math?
This is a deep question, and at some point I was talking to model theorists, and especially Boris Zilber, who is a leading figure in model theory, because in model theory it tries to classify mathematical problems in terms of hierarchies of difficulty, and this is not a P versus NP kind of difficulty, but a difficulty in the very underlying structures. Questions like, why is it that a polynomial over the integers is so much harder than to think about a polynomial defined over the complex numbers, even though the complex numbers is in some sense a completion of the integers. But why is it so much harder to look for models over integers? And at some point we were thinking that maybe the problems that we're going to encounter that neural networks will struggle with are ones that will go higher in this hierarchy of difficulty. But we haven't thought much more about this, but it will be very interesting to correlate this. But this is not computational complexity. There should be a new definition of a complexity in terms of how difficult a problem is. But it's hard to say how to define this.
Actually, just as an aside onto this aside.
An aside, yeah.
So there's a contest called the Summer of Math Exposition by 3 Blue 1 Brown, and it's about getting people to make animations and lessons for math, different math topics. We're doing one on this podcast, Theories of Everything, but for physics and also complexity and AI.
Oh, nice.
So physics, AI, and complexity. And this is a teaser of an announcement. It's not the full announcement, but those who are listening, it's going to be announced shortly, and there will be prize money for those who have the best explanation. The top 5 gets. You'll see.
Oh, I'd love to see that. Amazing stuff. All right, sorry. Back to BSD. So now finally I have to. So this is the memoration again. There's this was considered by it got Quanta interested, and Quanta considered this one of the breakthroughs of 2024 because because this was something that was AI guided, and it really surprised the experts. And just sort of, I want to tell you the story of this. Because it shows where we are in terms of AI assisted discovery. Probably my biggest contribution to this was to have insisted on this paper being called Memoration, because I remember this Skype that came through. This the original paper was in 3 years ago, when this pattern that appeared, and my collaborators were saying, this reminds me of this thing that birds do, and I said, oh, you mean murmurations of starlings? And then I was like, then I said, I'm going to insist that when this paper gets finished, we're going to call this paper the Memoration Phenomenon, and I kind of got stuck. That's probably my biggest contribution, because these are my collaborators are card carrying number theorists. We teamed up because they were trying to explore this AI assisted world, and I needed some real experts. So this already breaks it breaks the Birch test. The fact that I had to look for human experts to try to generate something like this already fails the Birch test, but it was worth it. It was worth breaking Birch for, because I made friends with these with number theorists, and it was something surprising to their community. Just a bit about the importance of the BSD conjecture. But this is kind of nice because it gives an opportunity for me to share my own ignorance on the BSD conjecture, because I learned about this as I was working not as a number theorist, which I'm not, but as an amateur number theorist coming from AI discovery side. So this is and it made me appreciate why the BSD conjecture is so important and why it's so interesting, and how surprisingly AI can help with this, and how the Birch test was almost met by this particular problem. So let's go way back to Diophantine equations. Diophantine equations, named after Diophantus, is just about finding rational or integer solutions to polynomials. I said these two are equivalent because you can always rationalize the denominator and cancel out. So finding solutions over Q is really kind of the same as finding these solutions over Z. So a typical example of a Diophantine equation is find all the rational solutions to this. And the solution this here is Pythagoras. So Pythagoras tells us, this is probably the most famous example, 3/5 squared plus 4/5 squared is equal to 1. If you think about it, this is actually highly non-trivial. The fact that, these have to square it up to 25 and just cancel to 1 is already kind of interesting. It's bizarre. But Pythagoras, and I can't remember whether it's Pythagoras or Euclid who gave the full solution to this equation. And the solution is that there is a one parameter infinite family of solutions of rational solutions. So the rational solutions are often called Q points, or Q for rational, or rational points on this quadratic. So what we say points because you can plot this, and this is thanks to Descartes. You can plot this, and this is a circle. So you're finding rational points on a unit circle. That's why the word solution and point is used interchangeably in this field called arithmetic geometry. This is great, but what I want to emphasize is that this is what's less known is that this is obviously just one solution, but there is a one parameter infinite solution to this. And so, in other words, all solutions can be parameterized in a specific way.
Mm-hmm.
So this is a quadratic case. If we recall high school algebra or a high school Cartesian geometry, a quadratic is what's known as a conic section. You're slicing the cone. If you bump it up, it's already extremely difficult. If you bump up the degree, it's already become an impossible problem. So instead of considering x squared plus y squared is equal to 1, oh, by the way, all of the quadratic ones can be solved in a similar way. So all the conic sections not over the complex numbers, but conic sections over the rationals can be solved in a similar way. But once you go into cubics, you're completely stuck. Even something simple like this, I change the 2 into 3. How do you find all rational points on this? We still don't know in general, in some sense. But you can see the kind of problems you can get. In Fermat, for example, is about talking about higher degree polynomials. Fermat's last theorem is x to the n plus y to the n is equal to 1, and find all rational points on that particular curve. That's it. And the theorem states that the only rational ones are are these the quadratic ones, and they're from 3 and above. There are no, so x cubed plus y cubed is equal to 1. There cannot exist any rational points, and so on and so forth. So now so these are called conic sections. That's just a curve, like parabolas and stuff like this, and circles and ellipses. Once it's a cubic, it's called an elliptic curve. There's a general theorem that, so you can imagine there could be more terms, right? Why not have something like x cubed, x squared y? That's also a cubic, is a degree 3, or x y squared, that's also cubic, and so on. There's a theorem by Weierstrass that all of these ones can be reduced after transformations of variables into this form. So you have a quadratic in y and a cubic in x, and then a linear in x. You can transform away all of the other coefficients if you wish. So this is called the general Weierstrass representation of an elliptic curve. This is I grew up in this one, and it's important to emphasize that my bias towards favoring over this is what exactly prevented me from being able to understand any of this from the AI point of view in the beginning.
Interesting.
Because for an algebraic geometer, this is the one that we always use, and it's like our favorite thing. We always trying to use something. And I will tell how an experiment failed playing with this, just because I was taught to always think in terms of Weierstrass form. This is a canonical representation of elliptic curves. And it's just, it's this in this particular form. It has no quadratic in x, and it has no other form, no linear, no cubics in y.
So just before we move on, this Weierstrass form, this means that any elliptic curve can be classified by these two numbers, G2 and G4?
Yeah, exactly. Yeah, there's a variable transformation that puts you into this canonical form.
Okay, so I know you'll get to it, but I'm interested as to why this prevented you, because I could imagine that these two numbers can serve as something like pixels or RGB numbers.
You're reading my mind. You're reading my mind. That's exactly the experiment that I tried and I failed. And it's in hindsight, it's not surprising how I failed. But I'll get to that in a minute. So let's park that idea. So just like canonical conics can be written into some kind of standard conics that we would remember from high school, the canonical cubic can be written into this Weierstrass form. The important thing about the cubic thing is somehow this cubic curve, and there's very deep reasons for this, captures a lot of the non-trivial arithmetic and number theory. For example, the Fermat's last theorem was able to be cracked because Frey and friends were able to reduce Fermat's. The Fermat, that's neither a conic nor a cubic, but they were able to reduce that to a particular elliptic curve called the Frey elliptic curve, and then Wiles comes in and proves the modularity theorem. That's a whole big story. So somehow this cubic is just at the intersection. That's why. Oh, by the way, cubics are great because this is an example. Well, this is the only example of a Calabi-Yau manifold in dimension 1. So there's something about Calabi-Yau, the elliptic curve, the cubic curve.
I see, right.
So all Calabi-Yaus in complex dimension 1. Remember the picture that I drew last time, where you have positive curvature is the sphere, zero curvature is the torus, and curves of surfaces of general type are negative curvature. This is the Euler-Riemann. What do they call normalization? The Riemann uniformization theorem. But the critical case: positive curvature, negative curvature, zero curvature, the torus. If you were to represent this algebraically, that's exactly this elliptic curve.
Okay.
So elliptic curves are Calabi-Yau manifolds of complex dimension 1. And this is just the critical part that also captures so much number theory. So that's why, so algebraic geometers, differential geometers, physicists, and number theorists are interested in Calabi-Yauness because of this intrinsic zero curvature. There's a lot of depth about this statement. A zero curvatured object gives so much wealth because it's just at the boundary of positive and negative curvature.
Oh, and that's what you mean by criticality, is zero curvature? Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack, Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.
Zero, yeah. It's the dividing point, and there's lots of conjectures. Yao has various conjectures on this about finiteness of this topological type in this space. But anyhow, back to so that's why I know about elliptic curves, because I came from this algebraic geometry, string theory background that also wanted to study this Ricci curvature flat or zero curvature objects. So back to this. So now it's a theorem, and this is a theorem due to so many people that have gotten the Fields Medal for proving different parts of this theorem. And this theorem really spanned a long time. People like Weil, Deligne, Grothendieck, de Work, Fountains, and Model, they all contributed to this. And the theorem is this. We can't say something like Pythagoras, which says that there's a one family, infinite family parameter solution to the rational points of the quadratic or the conic. We can't say something like that because it's too hard. But at least what we can say is the following: is that any elliptic curve over Q, of the rational points over any elliptic curve, it itself forms a group, and the group is of this form. The group is that there's an R infinite parameter family of solutions. These are called R is called the rank.
Mm-hmm.
So so how many copies of infinite solutions there are. And then there is this finite, what's called the torsion solution. There are 16 types of torsion. And this is really at the heart. All of this stuff, by the way, it's the heart of the Langlands. So you would have told Ed Franco would have told you about how excited he is about this sort of thing. But the one particular thing I want to emphasize is R, this rank, is the number of infinite family of solutions, and this R is the rank of an elliptic curve.
Yeah, this is the Mordell-Weil theorem, or the Mordell.
Exactly. You absolutely know. Exactly. Model Weil. Andre Weil. Yeah. Anyhow, so the reason I want to emphasize, there was still nothing to do with BSD, but this rank is the infinite number. It measures how many infinite family solutions over Q. So for in the case of Pythagoras, the rank, if you wish, would be 1, because there's one infinite family. So R is the generalization of 1 from the conic section case to the elliptic curve case. So that's it. This really is the state of the art in what you can say about rational points of an elliptic curve. There is this wonderful thing called rank, which is actually quite difficult to compute. It's not like I can just read it off. It's not like there's some analytic formula that says, I get this. I look at this form 1. This is x cubed y squared. I can just tell you the y rank is what I can't remember what it is in this case, 2 or whatever it is.
Sure.
Right. And the earliest experiment that I did was exactly as you said, as you suggested. Right. This is back in 2019. I just took a database of about 3 million elliptic curves in Weierstrass case. I took the two numbers G2 and G4, and then this was done. So this was a paper that I did with. So the reason is I did it with 2 data scientists who are using the fanciest data possible. And so we're all a bunch of amateurs as far as BSDs is concerned. Was to take the G2, G4 as 2 parameters and just plot them and then label them by R, the rank, and try to see a pattern.
Right.
We got a null result because this G2, G4 in the database, I can show it's massive. They're in the trillions. So it's very hard to get much. We had to take the log of all these numbers to even establish a plot. and the rank was so randomly distributed, even with the fanciest technology.
So what's the solution to this problem?
Plotting, yeah, we didn't see anything. It was just we couldn't get G2 and G4 to predict to any accuracy level what the rank is. But nevertheless, this was featured by New Scientist because it was such a strange and novel thing to do, even though it was a null result. But at least it was inching towards something. Somebody someday must be able to say something intelligible about BSD from a data science point of view. Anyhow, back to this. So what should be the thing to do? And this is where number theory expertise actually comes in. So first of all, this is an old law, which is if you can't solve a solution over the integers, solve it modulo prime, and see how far you can get. So, for example, I can't think of a rational number that I can't off the top of my head now. I think there exist solutions off the top of my head of a rational point on this elliptic curve, but at least let me try to work over modulo prime. So modulo 23, this is true. You can check it because 2 cubed is 8. 8 plus 16 is 24, and that is 1 modulo. So that works. This one works. You can see in the modulo 5, this works.
Yes.
So okay, this seems like a game, but the deep results of all of people like Deligne and Weil and all these people is that if you work over sufficient number of primes, in fact, if you worked over all primes and take a limit, you should know something very deep about its solutions over Q. And that's the point. So in particular, what you should record are these Euler coefficients, which is the number of solutions modulo prime, and how they deviate from p plus 1, the prime itself. So this is what's known as an Euler coefficients. Just keep track. Start with 2, and then try 3, try 4. Try 3, try 5, try 7, and then just find how many solutions there are. And this is a finite problem. You can just do, in the worst case, a grid search because you're doing modulo prime. You just have to count the number, and just check by brute force. So now what you do is to form what's called the local zeta function. The local zeta function is this exponential generating function that keeps track of the number of solutions over p. So you fix a prime, and you literally count the number of solutions modulo p.
Mm-hmm.
The more technical thing what you really should do is, because all finite fields are prime powers, what you actually do is to do an exponential generating function over the number of solutions over the field of prime characteristic p. But that's a technical side. But what you really should do, what you're essentially doing, is to keep track of the number of solutions of the elliptic curve, the number of not Q points, but the number of FP points modulo prime p.
Okay.
And the fact that this generating function becomes this polynomial divided by polynomial form is what got Weil, Deligne. When Deligne proved this, he got the Fields Medal for showing that it's in this particular form.
Interesting.
It's a very, very, very deep result in number theory. So, okay, long story short, is that when I met Oliver and Lee, they told me that whatever the hell I was doing with these data scientists, no offense to data scientists, we were just amateurs. We shouldn't have used the Weierstrass representation, because the Weierstrass representation inherently is not what an arithmetic geometer, what a number theorist would be using, that would capture the fundamental arithmetic of elliptic curves. So now there's the geometry of elliptic curves, which is my background. But that doesn't capture, the Weierstrass form doesn't capture that. The AP coefficients captures the arithmetic. So we should be using AP coefficients to predict the rank. So then we did, so instead of using a pair of very large integers, G2 and G4, and set up a neural network to predict R, you take instead the first, say, 100 AP coefficients. Now we're in a very interesting point cloud of a 100-dimensional point cloud. It turns out 50 is enough. It doesn't have 100 is just randomly chosen. You take the first 50 primes.
Mm-hmm.
Which is not too crazy now for by today's AI standards. Take the first, let's do 100. Take the first AP coefficient. Take the first 100 primes. Now take an elliptic curve, reduce this elliptic curve, and count how many solutions modulo these primes, and compute its polar coefficients. So for each elliptic curve, you get this 100-dimensional vector. Move to the next elliptic curve, a 100-dimensional vector. Now you just start labeling. Because of this wonderful thing called LMFDB, the LMFDB was set up by a bunch of people. I think Andrew Sutherland at MIT is one of the instigators of the Sutherland, and Booker and a bunch of people set up this thing, which just records everything you ever wanted to know about elliptic curves. There are tens of millions, on the order of 10 million in this data set. So now you've got 100-dimensional vectors as you march through. Because the LMFDB has the rank information, you can start set up a neural network. So we set up a neural network or some other classifier, and just like what we did with just like what I did with Alessandretti and Baronchelli on using G2, G4, this pair of Weierstrass coefficients to predict rank, that gave null result. And when we did this for 100-dimensional vector, this immediately gave 99.99% accuracy in prediction. You went from 0 to almost 100% immediately.
And you're using less data as well?
And using less data. Remember, with the data scientists, with the G2, G4, with these guys, we used something like all 3.5 million elliptic curves, and we couldn't get any accuracies at all. But with this one, even with 100,000, so you give me any elliptic curve, you just look at the Euler coefficients in this functional demands. I can tell you with almost 100% accuracy what this rank going to be.
Interesting.
So, of course, this immediately breaks Birch, yes, because I had to talk to real human experts who told me to actually use the Euler representation rather than the partial representation. But at the time, I was amazed. I was like, this is so cool. Of course, this is still useless for science. This was just a very, very cool thing to do in terms of visualizing elliptic curves. And then after some digging, we realized what really was under the hood that was happening. This is when Lee and Oliver were telling me, because they're number theory. So, he says, this is no surprise because this is the BSD conjecture at work. Somewhere under the hood, this is the BSD conjecture at work. So now I can finally define for you with the BSD conjecture. I will give you the weak version so as not to bore you for two reasons. One, the strong version is very too technical, and two, I don't even understand it very well myself. But the weak version simply says, if you take this generating function that keeps track of the Euler coefficients, form this product polynomial, now you take a product over all primes. This is what's called the local to global behavior, because you localize it. Remember, this zeta function is local to a particular prime. And now you take the product of all primes, you form this new function called the global L function. Now, I want to emphasize, this is called zeta function not because of abuse of terminology, because this is the Riemann zeta function if you work not over the elliptic curve, but if you worked over a point.
Okay. And
then this product is exactly the Euler product for the zeta function if you were to work over a point. But now we're more sophisticated. Our algebraic variety, our manifold is not just a point, but an actual elliptic curve. So it becomes a much more richer structure. So you get this L function really is, this global L function really is an analog of the Riemann zeta function. So that's why this whole Langland's business is so beautiful and so intricate, because it unifies geometry with harmonic analysis, with number theory, with all. This is why Eric Frankel was so excited about all of this stuff.
Right.
He was saying with such branch, because it unifies so many different branches of mathematics. Anyhow, so the BSD conjecture states, we don't know what the rank is. You can't do it by looking at the curve. But once you have the L function, by this strange procedure of working modulo over a fixed prime, and then take the product of all primes, you get an analytic function. Now we have an analytic function. I can start mucking around with it. I can use complex analysis. The order of vanishing of this analytic function at 1, this is exactly the rank. That's the BSD conjecture. If you can prove that the order of vanishing given any elliptic curve at 1 is this rank, then you get $1 million. That's the BSD conjecture.
All right.
Remember, the inverse of the Riemann zeta function at 1, the Riemann zeta function has a simple pole at 1, so its reciprocal will have a vanishing of order 1. Its order of 0 is 1 at s equal to 1. So it's a good analogy with the Riemann zeta function. But for elliptic curves, instead of a point, this one, the order vanishing should exactly equal to rank. So this gives you a way to compute rank, albeit a very, very convoluted and very, very intricate way to compute rank. But what surprised us was a neural network was able to predict this rank, this number, without going through any of this stuff, and predicted almost to 100% accuracy.
So where's your $1 million?
Well, there's no $1 million because 1, there's no proof, there is no statement, and so what? So we're still in as far as the Birch test, the A test is already failed because we had to talk to real experts. The I test has already failed at this point because there's no interpretability. So now how do we break the I test? And then surprisingly also break the N test. That should also be non-trivial, right? So that's why the Memoration Phenomenon was important. So then we got to know, we got this prediction. We were very excited. Oh yeah, it's always really cool. And then the excitement died down, and we're like, so what? What do we do? So this is the wonderful moment where you can recruit an undergraduate intern. So Alexei Poznikov was at the time a second-year undergraduate student of Qiuhuan Li's. But anyhow, so Alexei was given this thing like, dig under the hood and tell us what this neural network or this classifier, this base classifier or tree classifiers are actually doing. And finally, we homed in onto a PCA analysis, a principal component analysis, because basically we found that this rank prediction was doing so well with basically anything. Naive Bayes classifiers, neural networks of a very simple architecture. We didn't even have to go to transformers or encoder architectures. It's just a simple, forward feed linear structure with, I think it was basically sigmoid activation function was good enough to do this.
Uh-huh.
So, and PCA certainly would do it. So if you remember PCA, so PCA, I had to learn. I didn't know what a PCA was until 2017. PCA was just a principal component analysis. Here's a 100-dimensional data. Is a point crowding. I can't visualize it, so I find its eigenvalues and find the principal components of these eigenvalues, meaning like the ones that the data has the most variance of, and then focus and project onto these eigenvalue directions. This is like Stats 101, which I never learned. But luckily, I knew what a PCA was, so we were just mucking around with PCA. So here's the remarkable fact. If you take a PCA projection of this 100-dimensional vector space of elliptic curve Euler coefficients, you project it onto principal components. In this case, a 2-dimensional projection is sufficient to do it. You can see that the elliptic curves of different ranks actually separated it out, essentially, up to statistical noise.
Sorry, is it important that you do your principal component analysis down to 2 dimensions, or does it just happen to work out that way in this case?
So in our case, we chose 2 because it was easier to see. You would have done it if you project in any other dimension, you would see this kind of separation.
Sure.
Yeah. 2 was just nicest, and in retrospect, we really should have chosen like an Italian flag or a French flag, because it really just looks like a flag. In this one, this is elliptic curves of rank 0, rank 1, and rank 2. This is already quite interesting, right? It's still useless in terms of actual mathematics. It was very good for AI that, AI was able to just, there's not even really AI. At this point, it was just PCA analysis. It was just a data analysis in a picture that analyzed elliptic curves in a way that was never done before. This was 2020 when we had this result. So we look at this and we say, well, this is kind of nice. They're elliptic curves. They separated. Oh, by the way, elliptic curves. The ranks of elliptic curves is again a hugely, you can imagine, because of the BSD. So Manjur Bhargava was able to prove that almost all elliptic curves are ranked either 0 or 1 in the infinite limit, and he got the Fields Medal for that. So this is obviously a very, very important result. But in the NFDB, you do also have higher ranks as well. Just in the infinite limit, you will be vastly dominated by ranks 0 and 1. So they're either no rational points, no infinite families of rational points, or one parameter family, just like the conic section case. But the world record, I believe, is the one that's held by Normalkis, who discovered this rank 28 elliptic curve. It's huge. You can write it out. And that one is, so rank 28 means there are 28 parameter family, infinite families of rational points on that particular curve. But so in the LMFDB, you can already see there is sufficient number of ranks 0, 1, and 2 cases that there is this 3. I mean, there are rank 4s as well, but you won't see that in this picture. Now, so why do I emphasize on PCA? No, I'm finishing with this. Now, with PCA is because PCA is just a matrix projection. It's a linear transformation. You could look under the hood and just look at these matrices.
Okay.
And that's what we asked Alexei to do.
What does it mean to look under the hood at the matrix?
Because this is a PCA, just because this is a 100-dimensional vector, a point cloud being projected to 2 dimensions. So there's a whole bunch of 100 by 2 matrices. You can just look at, because nobody ever does this, right? You don't look at what the AI algorithm is doing. But in this case, you can just make people look at it. And so we gave it to Alexei to look at it, not expecting much. And this is an undergraduate. But Alexei expected all expectations. He really looked at a lot of sample these matrices and noticed that almost all of the non-zero values are focused on essentially just one row. That one row dominated vastly over any other. So what does that mean in terms of so that's interesting. So if you have a PCA projection, if you have a matrix projection that's focused on just one row, that means it's essentially you're just doing a sum. You're just doing an average in some sense.
Yes.
Right. And that's exactly it. So now what it's actually doing is that it's taking its Euler coefficients and averaging over a particular range of elliptic curves ordered by conductor, and I won't bore you with the details of conductor, and it's just computing this average. And if you do this average plotted against primes, you will start seeing this Memoration phenomenon. So let me just emphasize a few points on this. Right. First of all, you're taking, and this we wouldn't have done this if we didn't do a PCA analysis, or if we didn't do this machine learning exercise on rank, we wouldn't have dug under the hood in the first place. So that was already AI guided. And then it told us we homed in on PCA because we thought that might have been the most interpretable thing. And once we do interpret it, it gave this equation, which is a very, very simple equation, which always says just to do the following. Take families of elliptic curves, order them by this conductor range, and average over different elliptic curves, but at a fixed prime. This has come to known as a vertical average. It's a very strange thing to do because traditionally what you would do is to average for fixed elliptic curves average over different primes, right? Things like take the product formulas for a fixed elliptic curve and average over different primes. But this is the PCA told us no, you do the opposite. You take different elliptic curves over a range and average over a fixed curve, over a fixed prime, and plot the thing against prime. Once you plot it, you see exactly what this is. So the red bit are all of these 0 rank ones, and the blue bit are exactly all the rank 1 ones. So the reason that all of the neural networks and all of the stuff were able to fundamentally tell the difference between 0 and different elliptic curves was because they were oscillating in a different way. So
Okay.
that's why, because it's so striking.
Right.
You see this now. You can say, wow, it's guiding us what to do. It's guiding us. You can do this to all of the other ranks. You just plot, just isolate different ranks and plot them. And it turns out that all of the even parity ranks, all the even ranks oscillated in this way, and all of the odd ranks oscillated in the other way. Remember, there is 0, 1, 0, 1, 2, 3. They're all these different ranks. So fundamentally, you can tell the parity of the rank just by the way that these oscillation patterns happen. And this is the point. So, and then this was a plot that was produced by Lee and Postnikov. And Postnikov did this and showed us this. And then I remember this Zoom chat very well. This is 2021. So it was still like COVID times, right? So all we did all day was to Zoom people. And then it was like, and I think, my friends were saying, this is like, looks like what these birds do. And I say, it looks like Memorations. That's what it is, Memoration of starlings. And I said, well, we should absolutely call this phenomenon Memorations. We should instead of calling it a boring oscillatory pattern, we should just say this is a Memoration because it's not quite oscillatory, right? Because it's kind of, there's noise around it. And this noise is very interesting. I'll tell you in a bit. So this noise is part of the statistical error that you get from doing with finite data, because we only had 3.6 million whatever LMFDB. But the point was, then we immediately wrote to Sarnak and to Sutherland, who are the leaders in this field, thinking that, this is trivial. This is a trivial, this is a kind of typical kind of thing. You write to the expert and you get a reply within a day. And he says, yeah, this is trivial.
Right.
And it is a consequence of this theorem that I proved in 20 years ago in this paper. This is the usual story, 100 times it is this, right? But not only do we not get this message, we got a long message back from Peter Sarnak, who wrote this. What the hell, guys? This is bizarre that this pattern exists. So why, right? And then there was this many emails back and forth. I mean, to be honest, a lot of these emails way over my head, because my contribution was an AI guided algebraic geometry. I'm not a number theorist, so there's lots of back and forth, and then this became the Memoration Phenomenon, and then there were all these conferences organized. So we're back to this Birch test, right? So it failed the A because it wasn't automatic. We needed human. We were mucking around all the time with human experts. It passed the I test, right, because it became interpretable. This was a precise formula. Most importantly, it passed the N test. This is the first time that an N test was passed, because it actually galvanized a field of study in number theory. Now there's a whole field called Memoration Phenomenon.
Wow.
And I will. This is totally out of what the hell. I mean, this is above my pay grade, because I don't know the number theory community that well at all. So that's why Quanta was so excited. There were conferences organized in ICERM. There are all these people. There are workshops apparently in Bristol and various universities. They're like, oh yeah, there's this have a Memoration a workshop on this. So I'm not going to. I need to wrap up because I think it's getting too much detail. I want to tell you that there are other parts of this Memoration thing, and now, but now you can conjecture. This is a precise conjecture. This is a precise conjecture that was raised guided by AI explorations with led humans, and Peter Sarnak says it really well. He says this is a conjecture that Birch and Swinton Dyer could have raised themselves, but they didn't because they never thought to take this average. Because it's a bizarre thing to do. The AI doesn't know what it's doing. All it's doing is just spotting patterns. So, and just to emphasize, parts of this conjecture now of the phenomena, which is expected to be true for all L functions. So this is why. So in other words, the Memoration phenomenon should be a general phenomenon in the entire Langlands program. So it's now proven for Dirichlet character, the Memoration Dirichlet character has been now proved. So this memoration actually converges to a precise curve, and this was proven by, I wasn't involved in this because you need it was an actual number theory paper. And then Nina Zubriliana, who is Sarnak's PhD student, who was Sarnak's student, and then Alex Cohen, and now they proved it for weight 2 modular forms as well. And this was all in 2023. In 2024, and there are more results being precisely proven. And what it really is, and this goes back to Gauss and to Riemann zeta, is that this memoration fundamentally generalizes a bias in the distribution of primes. That's also quite striking. So this is an interesting fact. So Chebyshev noticed this factor before. So Chebyshev noticed, it's called the Chebyshev bias. If you take all primes, if you take primes and consider and find the remainder of these primes upon division by 4. Okay, you're going to get remainder either 1 or 3, right? Because you're modulo 4. And you would have thought that it's 50% 1 and 50% 3 in the large limit. But Chebyshev in the 19th century already noticed there's just a tiny bit of a bias towards 3 than 1. And that was just a conjecture of his. And this is, again, mucking around with data, this Platonic data. Like, why is it the primes are more biased towards one of the ones upon division by 4? This is known as Chebyshev's bias. And this was proven, actually, by Sarnak and Rubinstein in the 90s, but only conditional on the Riemann hypothesis being true.
Interesting, right?
There is this fundamental bias. So there's no unconditional proof of this, but it's conditional on the Riemann hypothesis that this is true. But this is what is interesting is that the memoration phenomenon is a generalization of this Chebyshev bias to all of the L function world. So it's a generalization from prime biases to the biases in all L functions, because there's this underlying oscillatory behavior. And that also has this deep relation with the BSD conjecture. So that's where this whole world, and that's why it passes I, it passes N. People are still working on it, but it doesn't pass A, because human expertise were constantly involved in interpreting, in choosing PCA. Anyhow, to wrap up this whole story, where are we, right, in terms of mathematical conjectures, in formulating problems in this top-down guided mathematical discovery over the centuries? And I will say that in the 19th century, the eyes of Gauss were good enough to come up with this conjecture. But the 20th century, BSD already needed a computer to come up with a groundbreaking conjecture. Yeah. And we are now just at the cusp, and that's why it's so exciting that AI-guided human intuition led to this DeepMind paper and led to the memoration thing and this new matrix multiplication matrix. So obviously, where we're going is a combination of these 3 directions. And I mentioned earlier, in these very rooms that I'm talking. That Faraday would have had the conversation with Maxwell in this room, about 150 years ago. Our institute has devoted one of our four themes to this AI for mathematical degrees, because this is really a paradigm shift in terms of how science is done. So just to promise, this is the last slide. So what is the current state of the art? Where are we with this AI guided thing? Now let's drop this human guided intuition for the time being. AlphaGO2 DeepMind has now reached silver medal. I think we had this long joke and discussion about how to beat the 16-year-old
Yeah.
the 12-year-old
Right.
Terry Tao. When you beat the 16-year-old Terry Tao, it's game over. That's a new age of scientific discovery. But we're making, like, these guys, or this field, we as a field, we as a community, we're making progress every couple of months. It's so fast. It's exponentiating. The DARPA, the U.S. military thing. Now that U.S. is defunding everything, but it will not defund military. So the military wing, the DARPA, which is the Defense Advanced Research Institute, I was just at a meeting with them 2 weeks ago, just launched EXP Math, where they literally are saying, exponentiating mathematics. You can Google this. The EXP Math project that DARPA is funding now is how to benchmark proving accelerating mathematics by proving. But unfortunately, they're not funding in this AI guided discovery area, which I think should be funded. And that's the way, combination of all these three directions. Anyhow, so that's AlphaGeo 2. AlphaProof, again, DeepMind, is on proving theorems at an almost research level. And I think we even joked last time that at the silver medal level, AlphaGeo 2 is high school level. AlphaProof is maybe college level, right?
Mm-hmm.
But this is the interesting one. I think this is just to wrap up, the EpochAI frontier math project, and you can Google this, and this is really on professional mathematical problems, the kind of problems you would give it to a colleague or to a researcher, a very advanced postdoc or graduate student, and they're benchmarking this now. In fact, I'm flying to Berkeley on Thursday to help. There's a whole team of us. We're flying in to benchmark their tier 4 problems, and this is happening this weekend, actually. So as of December 2024, EpochAI is capable of solving only 2% of advanced research level mathematical problems. But by March, they finished their tier 1 to tier 3 problems, and they gave this division of tier 1 to 3 problems and graduate level problems. You can go to this website to look how hard these problems are. And Terry Tao gave some problems, and Ken Ono. These are all really research problems. And I gave a problem to the tier 4, which is about to appear. And they're still soliciting more. And just go to this link. You can just look. Oh my God, this is a kind of problem I would give to my research student, or to the kind of problems I would work on with a collaborator, like that we would write papers about. And their benchmark is about 10 to 25% on tier 1 to 3. So once their next benchmark is tier 4, and tier 4 is so hard that humans are not likely to solve it, not because they're not because they're tricky, like Olympiad problem, but because they're actual research level problems. And we're actually together as a community are attacking this kind of problems. So this is where the state of the art is. So in terms of where the future of mathematics is, I think I try to summarize in this picture. So I'm using an old picture of Terry Tao because he's the best human mathematician.
Uh-huh.
And so how would it go? So you would have literature, the corpus of literature from scientific papers. You would go back and forth where human and I would process it together, and then use top-down mathematics to formulate conjectures from Platonic data that's gathered from the literature, or process it directly from the literature and formulate the kind of problems. Once the problem is formulated, you would go to auto-formalization, where it's only a matter of time before the lean community gets it. By auto-formalization, I mean you take a math paper in LaTeX and just hit return, translate it to a lean format. We're very far from that right now, having conversations with Buzzard, not because of the technology is not there, but because there's not enough lean data to train a large language model on.
Interesting.
We only have millions of lines of lean so far available. Just millions. We need billions in order to have, and it's millions of, these poor guys type in everything, right?
Yes.
So So conjecture formulation to this auto formalization, and then you go through and find pathways through MathLib in this bottom-up approach, where you would have a combination of LLMs, and that would generate your proof. And then you will feed to the human, where the human would actually interpret what this is, and then go back to writing the paper with AI and feed it back to the literature. This loop, I think it's where we are already heading toward. We're not. It's not in immediately in foreseeable future that all of this is going to be automated, but what is remarkable is that this is within reach, and I can't put a date on it. Maybe 10 years, maybe 5 to 10 years, because at every single step of this, we are being helped by AI. Like for example, the Memoration, which is taking available data and formulating it in this way. And already last week, I'm meeting people who are actually coming up with proof pathways by ChatGPT, and then humanly verifying that. So this is the brave new world of mathematics. I mean, of theory, of new discovery, and we're so lucky to be in this age where AI has advanced enough where it could actually help us with genuine new discoveries.
Yang, thank you so much for bringing us to literally the frontier, the bleeding edge of math, and also the future.
Oh, it's a great pleasure talking to him. Thank you for listening. I get very excited about this. So I'm parking everything else so I could devote to this new community, and it's a growing community of mathematicians who believe in this. And I think there's a recent quanta paper, the quanta report. I'm not involved in that one. That involved experts like Andrew Granville, who talked about what is a beautiful proof and how AI can help us with it, and that they are also amazed at how fast this is going.
Interesting. Thank you.
Thank you very much.
I've received several messages, emails, and comments from professors saying that they recommend Theories of Everything to their students, and that's fantastic. If you're a professor or a lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.